Welcome everybody to Power Corner. I'm your host, Alia Shokat, Editor-in-Chief of Power Electronics News. Today we're speaking with Mike Housholder, VP and GM of Thermal Management, and Jonathan Chien, VP and GM of Audio Interface at xMEMS. Welcome guys, it's good to have you here.
Nice to be here, Leah.
Likewise.
Thank you.
Well, let's start off by talking about xMEMS's story. And Mike, if you can answer this one. We spoke at CES, and you gave me a little bit of background, and you could talk about that in a little bit more detail. How did xMEMS start, and why did you guys leave after InvenSense was acquired by TDK?
Sure. Yeah, the core founding team of xMEMS got to know each other at InvenSense. That was a great MEMS success story, scaling MEMS gyros and accelerometers to billions of units. During the time at InvenSense, we had started to dabble into audio, MEMS microphones. After some left before the TDK acquisition, some stayed on, like myself, after. But the core founding team, kind of got interested in audio a little bit, but also wanted to focus on what was next in MEMS. The sensors industry has been well covered over the past few decades, and started to look at, sensors have done very well. What's next? And actuators kind of popped up there. So tying the interest in actuators with the other end, or the other side of the audio spectrum, speakers, they started to think, well, could these two technologies come together to build, the first really new type of speaker in over a century? So that was the underlying concept for the founding of xMEMS, which was, to create the world's first MEMS speaker.
Okay, thank you. That is very helpful to know. So I know that xMEMS has over 300 granted patents, so there's a lot of foundational IP. And maybe you could help me understand the underlying technology. And I know I'm assuming it's used for both the microcooling and the microspeaker technologies. There's a thin film piezoelectric membrane on silicon that flexes at an ultrasonic frequency when driven by voltage. Let me know if I'm wrong. Are these actuators used for both the technologies, microcooling and microspeakers?
Correct. It's the same fundamental piezoMEMS platform, and I think you captured the technology well. It's conventional MEMS processes with an added step of depositing a thin film piezo material. Thin film piezo materials came about roughly around 2015, and became production viable around 2018 or so. So we kind of piggybacked on those innovations and that platform to build our speaker and cooling platform.
So, what's the story behind the underlying technology? How was it first developed, and how did it morph into was it a sound actuator first and then and then cooling, or was it cooling and then sound?
Yeah, so interesting story there. So we founded the company to create a speaker. And so we start with the fundamentals of the platform. Okay, we need a piezo material with enough displacement to actually move enough air to create a robust and loud sound. And we knew, and Jonathan will get into this later with the invention of our PulseAir speaker technology, but we really needed to become an ultrasonic transducer, and place some, make some really unique innovations there, in order to produce enough bass for rich full bandwidth audio. You can't just push air like a conventional speaker with MEMS, because you don't have enough displacement. So we knew we had to develop a transducer using piezo materials that could generate very high sound pressure levels at low frequencies, because again, it's all about the bass, so to speak. and conventional approaches to MEMS speakers where you're just pushing air, you'll never produce enough bass for conventional audio products. So looking at those fundamentals and looking at the approach of this ultrasonic transducer with kind of an amplitude modulation approach, got us to a speaker that could produce theoretically, and we've actually proven it now, really good bass response. But as we looked at that architecture, and we hadn't even figured out how to make it work yet, but we looked at the fundamentals of high sound pressure levels at low frequencies, say around 20 hertz.
Yeah.
And we said, well, does that extend below 20 hertz?
Mm.
And essentially, the answer was yes. So the thought came up. Well, eventually you're getting to 0 hertz DC, which is a net airflow. So the founders thought, well, maybe someday if we are successful in making a speaker, we might also be able to make a fan or an air pump.
I see.
So way back in 2018, even though we founded the company to produce speakers, the first patent we ever filed was on the concept of this microcooling.
Okay. Okay.
We had no idea how to build it yet, but we said, okay, that's a good idea. Why don't we patent it? And when we figure things out on the speaker, we can come back to this at a later time. And that's kind of how it all panned out. The speakers came first, and then once we got that nailed down, we could produce the cooling.
Okay. Okay. Gotcha. But the cooling was the first patent. Uh,
Correct.
okay. Gotcha. Very cool. I wanted to understand the design optimization for each of these. How do they diverge? The kind of, how do you tune the chip for maximum sound pressure level, as you were saying, at low frequencies, versus one tuned for, say, maximum airflow?
Well, a little bit of that is in the in the IP of the company, but
Yeah.
but essentially it is, we do have the benefit of having the same core platform
Mm.
and very similar design fundamentals. But one is tuned for AC, 20 hertz to 20 kilohertz,
Mm.
and the other one is tuned for DC airflow. But it's the same fundamental piezoMEMS platform.
Okay.
They're produced on the same line at the same fab.
Yeah.
Just slightly different design fundamentals that I'm sure you want to get into, but I'm not going to I'm not
Don't
going to
worry.
disclose.
I wanted to get into that, and then I saw the monumental task of going through 300 patents, and I thought, okay, let's just talk about the baseline technology. Um, um, I appreciate you going into that detail. The fab that you work with, it was Bosch, right? You guys have a relationship with, or was it
Well, our
yeah,
our first fab was TSMC,
TSMC?
and
Gotcha.
and that was a natural fit for us because
Yeah.
that was our primary fab back in the
Yeah.
InvenSense days.
Yeah.
So that was a natural, established and successful relationship.
Mm.
But now, as we've matured as a company, we have two discrete product lines. The customer interest is growing quite rapidly. We do
Yeah.
need to expand capacity. So yeah, we have brought on Bosch as our second fab, and we can
Yeah.
produce both speakers and cooling at both fabs.
Okay, great. Okay, thank you. So I was thinking we could talk about more specifically the microcooling technologies, um, and we could talk about how they diverge from traditional motorized fans, say, axial fans in terms of performance.
Sure. Now, obviously, the conventional axial, rotating blade fan's been around for quite a long time.
Yeah.
Copper coil, magnet motor. Um, Fundamentally, fans are really good at high CFM, high
Mm.
airflow, but typically static pressure, back pressure is their weak point. They need access to ambient to produce their airflow and performance. Um, our MEMS fans, our MEMS microfans, are obviously quite a bit smaller.
Yeah.
Um, and instead of rotating blades, these
Mm.
are MEMS structures that are oscillating up and down in
Yeah.
a 1 millimeter thin silicon package. So this is an all silicon MEMS microfan. So we're never going to displace as much air as a conventional rotating blade fan, but the fundamentals of this piezo MEMS architecture, you can think, even though we call it a fan to familiarize people with what its function is. Fundamentally, it's an air pump, and pumps are really good with generating very high static pressure, because again, we need high pressure to generate sound. We need high pressure to generate a net airflow in this very thin silicon platform. So we are lower CFM but high back pressure, but that serves our markets very well. Rotating blade fans serve their markets really well, but they can't fit in a smartphone. They can't fit in smart glasses. They don't fit in tight spaces very well. We do. We're 1 millimeter thin silicon solid state component. And also, we're going into these devices that are very tight on space.
Yeah.
So the necessity to not just generate good airflow, but also to generate airflow with enough static pressure to overcome all the resistance in the system. We're going into smartphones with, that's a very compact mechanical and electrical design. Glasses, very compact mechanical and electrical. We need to be able to move air through very tight spaces.
Yeah.
And even if you could fit a conventional fan in those products, you really can't move air through those tight spaces without risking stalling the fan. So, a fan might need to be right on the outside surface of the phone. We can basically be embedded deep into the electronics of the phone with a very, very small, microns thin duct channeling out hot and cold air through the device.
That is very helpful, and so many questions have come up that I want to learn more about. Is there the is there a trade-off, like a design trade-off, as they were saying, with airflow and back pressure within the MEMS itself?
It's we kind of get what we get with the platform.
Yeah.
And again, just the fundamentals of the platform give us a really high static pressure, and we fight for every bit of airflow that we can get. But with everything, we're trying to optimize for silicon area, small silicon area, maximum airflow. But the back pressure, actually, if you look across our products, and we'll get into that later, all of our products basically have the same relative static pressure. So as we go smaller die size, larger die size, the static pressure stays the same. The only thing that changes is the airflow, higher versus lower.
I see. I see. It seems that the airflow is directly correlated to the footprint, the die size.
Correct.
Okay.
Correct.
Okay.
Smaller die size, less airflow. More die size, more airflow. But the
Okay.
static pressure stays the same.
And in terms of differences, I imagine there's a significant lifetime difference with motorized fans versus the MEMS platforms.
Correct. Yeah, being solid state
Yeah.
and having semiconductor level reliability is definitely our advantage.
Yeah.
As with anything, we have to dust proof, we have to waterproof, but our fundamental silicon is IP58 rated with no special treatments, and then you apply conventional mesh to get to higher levels of water and dust resistance. So we can achieve an IP67, IP68 rating, which is common in most modern smartphones.
Yeah.
We take the major step there at the base silicon level, getting IP58, and then with mesh get to IP68. So very robust to dust and liquids. And then just the solid state nature of this gives us a very long lifetime. So even at elevated temperatures, we can produce a device that can have a lifetime, 24/7 operation, north of 9 years.
Okay. What may I ask? What is the mesh that allows for that IP67, IP68 rating?
Yeah, they come from a variety of vendors, but these can be oleophobic type meshes.
Okay.
Their suppliers, Gore, Sati, many others that provide these meshes. They're already in use today in smartphones, in earbuds, all types of consumer products.
Yeah, I didn't know, so that is helpful to understand. I had another question around there was a lot of great demos at CES when we met, and the one that struck me the most was the delta T, or the kind of difference in open air versus an encapsulated environment like the smart glasses. And it seems like mounting and routing airflow is half the battle. Do you have any examples of how xMEMS has helped customers in specific applications with that?
Yeah, I think each application brings new challenges just in
Yeah.
terms of mechanical form factor, space, and whatnot. So we have a team of thermal engineers on staff. These are mechanical engineers with a thermal focus. And we look at this on an application by application basis. We work with the customer, understanding their mechanical design constraints, and we'll define an airflow path, ducting, channeling that addresses the heat source, but also has an efficient channel for air ingress and
Mm,
hot air escape.
mm.
So
Yeah.
that takes a shape of thermal modeling, at a CAD level.
Yeah.
And then once the results meet the customer's expectations, they can take that CAD and build their first functional prototypes.
So you guys are able to help the customers with their specific form factors, and build
Yeah,
to their specifications as well.
and it's been kind of necessary, because even though we're
Mm,
dealing with really sharp thermal engineers at our customers,
mm,
they've been working with conventional rotating fans their whole life, high
mm,
CFM, low back pressure. So if they apply that same assumption to our device, they don't always get the best results. So
mm.
we need to teach them how to make use of the high static pressure combined with our CFM to get the best results.
That is interesting. I am curious how that changes things design wise and layout. But I imagine that's a question for the thermal engineer and that that you work with. Um, So when we talked last, you did mention that there was customers were sampling microcooling for ECUs, in potentially automotive applications. Have you seen any movement there? And are there any kind of changes when you move microcooling, say, from a phone to a vehicle?
Um, yeah, a little bit. I think, right now we're really focused on our consumer launches in phones, glasses, SSDs, but we have planted some seeds in automotive. I think, as you start an automotive engagement, and that's a 3 to 5 year engagement before it
Yeah.
reaches production. So we've planted some strategic seeds there with some tier ones, recognizing that this is going to be a long-term development that will turn into to nice revenue for us and be good steady revenue for us long term, to kind of balance with the up and down of the consumer market. But in the automotive space, yeah, ECUs are definitely a strong application. We've seen LED lighting as
Oh,
another
yeah.
interesting approach.
Yeah.
Um, and then there's just infotainment devices
Yeah.
in the cabin that are also of interest.
Yeah. Very interesting. And maybe we could talk about the data center applications. I know there's the different tiers, right? And the one of the higher footprint ones, the XMC 4800, was aimed at data centers and density systems. There was some information on using microcooling and optical transceivers that you announced last year. Is that a separate effort? Could you talk a little bit more about the data center cooling aspects of xMEMS?
Sure. I think with the data center, we're going to lead with SSDs. We already
Yeah.
have lead customers in that space, so we'll launch in SSDs first. I think the next promising application is going to be optics and primarily lasers. So I think, while most optics in data center today is pluggable optical transceivers, we are moving towards near packaged and co-packaged optics,
Mm,
where a lot of the electronics is moving closer to the CPU, GPU, and fitting under the cold plate.
mm,
But what is not moving in that direction is the laser. So the lasers are still pluggable because they're a high failure device,
mm.
with a lot of sensitivity. So those are staying pluggable while the rest of the transceiver electronics move towards the cold plate. So I think we're looking at microcooling for the pluggable lasers as that next core market for us. But in general, as the data center moves to liquid cooling, there will be some lower power subsystems that kind of get orphaned. They're not valuable enough to move under the cold plate,
Yeah.
and there's no system fans to serve them critical airflow anymore. So having strategic, very targeted spot cooling from a microcooling device might be the solution there.
Very cool. We could move on to the XMC 1200, the new release. And the release calls it the world's smallest active microfan at 46 millimeters squared, right? And it's got that dedicated companion ASIC, the Astra 2. Could you talk about this release in a little bit more detail? Is the new ASIC specific to the 1200?
Yeah, so from the ASIC perspective, we're fortunate enough to have that ASIC serve our entire roadmap. So that can drive the 4800, the 2400, and now the 1200.
Okay, okay.
So yeah, one single ASIC serves our roadmap. The 1200 was developed really based on guidance from our existing glasses customers. So we do have some design-ins with glasses customers with our 2400 product.
Mm.
And the 2400 is directly addressing the processor or the SoC. A lot of
Okay.
these glasses are now moving to augmented reality where they've got a light engine, either single light engine on one side or dual projectors. And that is a much smaller, it's placed kind of in the front of the glasses with a very small mechanical size constraint.
Mm.
So customers are using the 2400 today for the SoC, but they needed something smaller to cool the light engine. And we
Yeah.
want to cool the light engine for color and wavelength stability as that display runs over time, generates more and more heat. So the 1200 was really guided by those customers to really fit the light engine. But as we segment out the smart glasses market, I think the 2400 will continue to serve kind of the
Glasses.
higher end SoCs.
Mm.
But as we get to kind of smaller, thinner glasses that may have reduced functionality, the 1200 may also serve maybe the lower end of the SoCs, where the 2400 is reserved for the higher end SoCs.
Okay, that is very helpful. Um, I was wondering because you're as you were explaining earlier, you have that same base microcell. I saw there's a recent electronics cooling piece on this, and the engineer mentioned there's a 1x2 array for the 1200, 2x4 for the 2400, and 4x8 for the 4800. Could you talk about that in a little bit more detail? Does each array say require its own tuning for airflow or back pressure targets, or is it kind of like a basic scaling type?
Yeah, luckily the scaling's relatively simple and efficient.
Yeah.
So we can take that base cell and scale it, and multiply it up or divide it down, and get a pretty linear, make some pretty linear assumptions on how the airflow is going to scale. But as we've learned with multiple generations of our speaker products, we also have the opportunity to change the aspect ratio of that cell.
Mm.
So we can make it longer and thinner. We can make it more square,
Yeah.
to target different markets, different applications, different form factors.
Yeah.
But I think we've kept it pretty basic in this first phase of our roadmap with the 1200, 2400, and 4800, just kind of scaling that base cell up and down. But as our roadmap expands, we may see different aspect ratios and form factors.
Yeah, it makes sense. Do you have, off the top of your head, the airflow and the back pressure specs for the new XMC 1200?
Yes, of course. Yeah, the 1200 is 10 cc's per second of
Mm.
airflow and about
Yeah,
1100
same.
pascals of back
Yeah.
pressure.
Okay. Okay. Um, I only one more question really for you that, Mike, thank you so much for the time that you've taken to answer these questions. I scanned the patent list and I saw a patent for active two-phase midstream cooling. I thought that was very interesting, and it kind of sounded like a mini spray cooling system. Is this something that we might potentially expect in the future as a potential product?
We come up with new ideas all the time. But
Yeah.
I mean, one question we constantly get
Yeah.
is, can this micro pump architecture be retargeted for liquid cooling. And that patent you're referencing isn't exactly liquid cooling. It's more of a two-phase type approach. But yeah, we're constantly looking at ways to scale this platform and address new markets. That patent is certainly one idea that may or may not see the light of day. But we've got a lot more in the works behind
Well,
the scenes.
it's definitely exciting to see, and it's great to see that there's a lot to, I guess the base technology can be used for a lot of different a lot of it applies to a lot, I imagine. So
Yeah, we've got some of the best MEMS engineers on the planet, and
yeah,
they're always thinking in the back of their minds, what can we do next? So
yeah,
that's part of the fun.
yeah. Very excited. Well, thank you so much. These are all the questions I had for microcooling, but let me know if you had any thoughts, anything that you wanted to share that it was important to mention in regards to the microcooling technologies.
No, I think you covered it quite well today. Thanks for the time and the good questions.
Great. Well, I'm gonna shift here to Jonathan, and we can talk a little bit about the microspeaker technology. And Mike, if you wanted to chime in at any point, please don't hesitate to. We could maybe start off, Jonathan, with how the piezoMEMS technologies, the microspeaker technologies, how do they differ from coil and magnet solutions, like balanced armature and electrodynamic speakers and key specs like sound pressure level and solution size.
Yeah. All right. Yeah, I think that's a good place to start. And so we'll stage the microspeaker loudspeaker discussion later, but let's just first
Yeah.
talk about the piezo-MEMS speakers in general. Well, at the sound output level, piezo-MEMS and the conventional coil magnet speakers, whether it's balanced amateurs or electrodynamics, they follow the same physics principle. The sound propagates through compressions and refraction or decompression of air, and that the change in the magnitude and frequency is what produce sound pressure level, or SPL. All right. Well, where the technologies start to diverge is the mechanical structure under the hood. A conventional speaker that uses coils and magnet, to move a diaphragm up and down, right? Where a piezo-MEMS speakers instead uses a piezoelectric effect to flex a thin film, a silicon structure, much like a flap. This is what is called MEMS, it's microelectromechanical systems. We use that structures to move airs. And so I think the difference that had the biggest consequences is that because the moving structure is a piece of silicon, and so it doesn't warp or break up the way that paper or plastic diaphragm does. It's got a much 10x of the stiffness ratio. And also with no magnet in the systems, where you could make these the entire speaker package that's very, very light and compact, and 90% lighter and 70% smaller than a conventional speakers. And as I think Mike has talked about that, it's something that we should not overlook, is the solid state uniformity. We built these speakers on standard semiconductor process. And so this is the same solid state precision that transforms sensors and memories. And so when you bring that to speakers, it means that we can control these speakers in high volume with far tighter part-to-part consistencies in SPOs and phase matching than you can get by binning dynamic speakers on an assembly line.
Okay, thank you. Ed, you already mentioned this, but there's the microspeakers and the loudspeakers, and I tried to make a bit of a table. I noticed that there's a lot of nature inspiration for the names, and I liked that. I maybe you can explain, what's the difference between the microspeaker and the loudspeaker lineup?
There really isn't a universal defined what's a microspeakers or a loudspeaker. So let me share how we use them at xMEMS to keep things simple for the device manufacturers. All right. So we categorize microspeakers as a driver that used primarily as a tweeter, It's typically used in combinations with a electrodynamic woofer in a two-way systems, right? You get the woofer responsible for the lower bandwidth, and then you use a tweeters for maybe 5K and above. And so you could find these use of two-way systems in your monitors, premium earbuds, or high-end headphones, really there to compensate for the high frequency decay that's the characteristics of a electrodynamic woofers. Okay. Then what we define as a loudspeaker is a full bandwidth single driver solution that can cover anything from an open ear, like a open fit earbud, to an AI glasses, more of a near field, and all the way up to something that's arm's length, free field mobile devices such as mobile phones or tablets. And this is where xMEMS technologies, the sound from ultrasound technology of our PulseAir speakers start to make the biggest difference because it delivers the required loudness in the most compact footprints in this category.
Yes. Maybe we could, can we talk about the sound from ultrasound xMEMS solutions, with a deeper dive in the PulseAir speaker category? So there's the Cypress and the Sycamore. That's a part of the PulseAir portfolio, and that's PulseAir is the new name. It used to be sound from ultrasound. Can you talk about that? What features and benefits does it offer to audio designers?
Yeah, sure, of course. Yeah, so you're right. Cypress and Sycamores are both in the PulseAir speaker family. They're the world's most compact and lightest loudspeakers designed for fashion-forward wearables. And I'll explain that in a few seconds. PulseAir works on a completely different sound generation principles. It builds on the same piezoMEMS technology, but instead of actuating at the fundamental audio frequencies, it actually generates sound by demodulating hundreds of thousands of air pulses per second. And that's where the name sound from ultrasound comes from. The biggest benefit of constructing sound from ultrasonic air pulses is that now we're not limited by the fundamental frequencies. We'll be able to oscillate and move air volume at much more air volume within the same footprint, and we can make a full range loudspeaker extremely compact and light. And so now, today's consumers wants their wearable not only sounds good, but fashionable, looks great, comfortable to wear all days. And so for the first time, product designers have a different kind of loudspeakers that actually adapts to their industrial design and really unlock their design creativities. And that's what PulseAir means to our customers.
Thank you. Maybe we can move to the microspeaker lineup. From what I understand, we've got the Mir, the Cowl, the Montera, and they use a direct piezo drive in the audible band with the Aptos 2 amplifier, and that's the companion IC. And then there's the last end that also uses a direct piezo drive, but with no amplifier at all. Could you talk about that lineup a little bit more as well?
Yeah. Well, you got the lineup right.
Okay, perfect.
Great. Yeah. So our lines of solid-state microspeakers delivers pro-grade and reference quality sound, and starts with Cowl, which was our first compact tweeter in a 6x3 millimeter package. The gamers and audiophiles in particular really appreciate the superior sonic accuracy and the dynamic impulse response. It's amazing how microseconds of difference, how microseconds really make a difference for in the gaming applications, and also how it reproduces, audio instruments. After Cowl, we follow with a device called Mir, where we push the package down from 6x3 to 5x3, and also cut the power consumption by about 30% without sacrificing SPO. Then with the Montera Plus, we go in the other direction. It's a larger die where we push the output in a coupler up to about 127 dB of SPO. And that was our first attempt, xMEMS' first attempt to try to push towards from a microspeaker to a loudspeakers, where we could actually start to use a single MEMS speakers to drive a well-sealed in-ear monitor on its own. All right. Now, because these are piezoMEMS speakers, they're capacitive low. And so these speakers draws very little current, but needs a high voltage to drive the transducers. And so we designed a companion high voltage amplifier called Aptos 2 that swings at 30 volt peak to peak to pair with these micro speakers. Yeah.
And so the last end, that one removes the stage entirely, right? And is that also driven by any specific ASIC technologies? Could you talk about that a little bit more?
Yeah. Just to close the loop on that, for a more price conscious segments, product that still appreciates the high frequency boost, we tweaked our MEMS process to create lessons, and it can actually be driven by an audio subsystem in a Bluetooth SoC. So essentially, there's a Class H or Class D amplifier is embedded in audio SoC with a 3 volt swing. Then you'll be able to use that to drive lesson directly without any external amplifiers.
Thank you so much, Jonathan. I don't have any further questions, but is there? Well, actually, there was one question. Beyond wearables, do you see any other applications for microspeakers and loudspeakers?
Yeah, so I think we cover the wearables space pretty well with both the solid state microspeakers and the PulseAir speakers. But as we get into the loudspeaker applications, then you start seeing interesting extensions on both extremes of form factors. On a smaller form factors, we've seen interest in putting the small drivers in potentially a joystick for examples, or potentially put it in a trackers. You can see how AirTags is a certain size today. Imagine you can make that thinner and smaller and still deliver a full frequency audio tracking signals. That would be pretty interesting. And then on the other side, moving towards bigger devices would be in a mobile space, for mobile phone, tablets, and potentially in the future laptops.
Thank you so much, Jonathan, for your time. Was there anything that you wanted to mention that I might have missed as well? Any closing thoughts in regards to the speaker technology?
Well, I think you covered all the bases pretty well. I would just say that the PulseAir speakers or the piezoMEMS product family is a new categories of speakers, and so we're working with the industries and customers to educate them on how to take advantage of these speakers to build not just another audio devices, but something that really could adapt to their design languages and make beautiful and more comfortable product going forward.
My last question was really, I know we talked about the new release, which was the XMC-2400, but what might be next on the roadmap? Anything that we hadn't covered yet?
Yeah, I think from the cooling perspective, yes, we're going to continue to expand the product line to serve more markets. We've got some great core markets in phones, glasses, SSDs established, moving towards optical and some other markets, but we'll continue there's much more we can do, and we'll expand beyond that. I think just in general for xMEMS across all of our product lines, the industry trend towards distributed AI is obviously going to serve us very well, because what MEMS does well is shrink and make things smaller and lighter. So as AI distributes to the edge, into glasses, into phones, into wearables, you're going to need audio that is thinner, lighter, smaller, because these things are going to be on our body all day, and they need to be lightweight. And then because they're going to be having a high duty cycle processor processing AI in the background, that higher duty cycle is going to generate more heat, and you're going to need very thin, very light cooling. So I think this piezoMEMS product line between audio and cooling will serve the industry trend towards distributed AI at the edge.
Mm. Yeah, I think that's absolutely fascinating, and what a prime time to be, spearheading the solid state sort of actuation, technologies. It definitely seems like there's a lot of opportunity there. So very excited to be speaking with you guys, and I'm really looking forward to seeing what's next.
Thank you so much for your time.
Yep. Thank you, Lee.
Thank you.